Mathematics at the basis of the universe. Stranger things have happened, and perhaps the strangest and most amazing of all is that mathematics was able to be mastered by a creature related to the monkey. Eric was the development of mathematics, physical and mathematical science, not because we know so much about the physical world, but because we know so little we are able to discover only its mathematical properties. Bertrand Russell. The intellectual abilities of Homo sapiens, if they have changed over the last 100,000 years, then not so much. Place children from the era when mastodons and woolly rhinoceroses roamed the earth in a modern school, and they will develop no worse than their peers from the 21st century. Their brain would be able to master arithmetic, geometry, and algebra, and if they wanted, they could well study the subject in depth and then become professors of mathematics at Cambridge or Harvard. In the course of evolution, our neural apparatus developed the ability to perform complex calculations and comprehend such things as set theory and differential geometry, and long before such abilities were put to use. By the way, there is a certain mystery in this. Why do we need this innate talent for higher mathematics if it has no obvious benefit for survival? And on the other hand, the human race appeared and survived because man surpassed his competitors in intelligence, the ability to think logically, plan ahead, and ask himself the question, what if? While inferior to other species in speed and strength, our ancestors were forced to rely on resourcefulness and the ability to calculate the situation. Logical thinking became our only superpower, and from it over time developed the ability to complex communication using symbols, rational interpretation of the world around us. Like all animals, we successfully perform complex mathematical calculations without thinking on the fly to perform even the simplest actions to catch a thrown ball, or avoid meeting a predator, or get game. You need to very quickly solve many equations, try to program a robot to perform such actions, and the complexity of these calculations will become obvious to you. But a huge advantage of a person is that he is able to move from the concrete to the abstract, analyze the situation, ask yourself, what will happen if you plan in advance? The emergence of agriculture arose the need to clearly track the change of the seasons, the development of trade, and the emergence of settlements gave rise to the need to make transactions and keep records, both for compiling calendars and for conducting commercial activities. Some kind of calculation system was needed, and here elementary mathematics was born. One of the regions where it began to rapidly develop was the Middle East. Ceramic chips found by archaeologists. Sumerian traders date back to the 8th millennium BC, and show that even then people had mastered the concept of numbers. Although at that time they did not yet separate the concept of number from the objects themselves that needed to be counted, tokens of different shapes were used to count different objects, such as sheep or jugs of oil. When exchanging a large number of chips, they were sealed in special clay containers, bull, and to check the contents, the bull had to be broken later. They began to put marks on them indicating how many chips were inside over time, from such symbolic images. A system of recording numbers was formed, and the chips themselves began to be used as a primitive form of money. Along the way, the concept of number separated from we count them objects, so that, for example, 5 remained 5. Whether it was goats or loaves of bread at this stage. Mathematics seems inextricably linked with everyday reality. Counting and accounting applied tools of farmers and merchants, and if these methods cope with their task What difference does it make what concept underlies them? Simple arithmetic is inseparable from what is happening around us. Sheep plus sheep, 2 sheep, 2 sheep plus 2 sheep, 4 sheep. It would seem that nothing could be simpler, but think about it, and you will understand that something strange has already happened. When we say sheep plus sheep, we assume that VC are the same, or at least that the differences between them do not matter when calculating. But sheep are not all the same, that is. We separated from sheep 100 quality that unites them and distinguishes them from other objects, and then performed on it actions using another abstraction which we call addition. This is a serious step in practice. To add one sheep to another, it is sometimes enough to simply let them graze in one field. But from the same practice we know that all sheep are different, and if we dig deeper, what we call a sheep, like everything else that surrounds us, is an integral part of the universe. In addition to this, it is a little disturbing the fact that what we perceive as objects of the surrounding world, take at least those same sheep, in fact, are only a product of our mind, brought to life by signals affecting the senses, even if we assume that a sheep exists objectively. From physics we know that it is a complex temporary collection of elementary elements in constant motion, particles, and yet counting sheep we are able to somehow ignore all these complexities, or, more precisely, not even be aware of them in everyday life. The Egyptians had a good command of practical mathematics and successfully applied it, and during the construction of the Pyramid of Khafre in Giza. Of all the disciplines, mathematics is the most accurate, and unshakable natural sciences and other areas of human activity represent at best some approximation to the ideal, constantly change and evolve. As the German mathematician Hermann noted, dumbbell in most sciences. A new generation destroys what was created by the previous. What was established by one is cancelled by another. Only in mathematics each generation adds a new floor to the previous building. This is its difference from all other sciences. Inevitably, it is embedded in its very essence. After all, mathematics begins with the fact that the mind extracts from what is given to us in sensations only those knowledge which it defines as the most fundamental and unchanging. This leads to the emergence of such concepts as natural numbers, addition and subtraction, allowing us to measure the number of objects, increase and decrease it. The abstract concept of quantity 1, 2, 3, and so on is perceived as a common feature of different sets of objects, regardless of what these objects are and how much different from each other individual objects of the same type. Therefore, such a quality as immutability, inviolability, is inherent in mathematics initially, and is its most important advantage. Mathematics exists, no one doubts this. Say the Pythagorean theorem, it is after all part of our reality. But here, where does it exist when it is not used and not embodied in some material form, and where did it exist before, thousands of years ago, before it came to someone's mind? Platonists believe that mathematical objects such as numbers, geometric figures, and the relationships between them exist independently of us, our thoughts, language, and physical universe. They really don't specify in what kind of non-earthly spheres these objects live, but they are convinced that they somehow really exist. Most mathematicians, admittedly, share this point of view, which means they believe that mathematical truths discover they invent. It's fair, however, that most mathematicians most likely don't care about all this. Philosophy suits them quite well, just doing science, just like most physicists. Both those working in laboratories and those solving theoretical problems are unlikely to care about the problems of metaphysics and still understanding the true nature of things. In our case, mathematical objects is an interesting activity, even if we are not destined to find the final answer. Russian mathematician and logician Leopold Kronecker believed that man was given only whole numbers by his expression whole numbers. God created everything else is the work of human hands. English astrophysicist Arthur Eddington went even further, saying mathematics does not exist until we create it. People will probably continue to argue about what is mathematics: discovery, invention, or perhaps a combination of one and two generated synergy intelligent matter. It is unlikely that there is a simple answer to this question. One thing is clear in mathematics: once proven and the position forever becomes the truth, not allowing for disputes and not confirmed by the influence of subjective factors. I love mathematics, Bertrand noted Russell, because there is nothing human in it, because nothing in essence connects it with our planet or with this entire random universe. David Gilbert expressed a similar thought: mathematics do not know once and geographical borders. For mathematics, the entire cultural world represent a single country. This is impartiality, universality of mathematics, and the most important advantages, which, however, does not in any way diminish its aesthetic appeal. For a person with a trained eye, beauty is the very first criterion, for there is no place for ugly mathematicians in the world, said the English mathematician Godfrey Harold Hardy. The same idea, but from the point of view of theoretical physics, was expressed by Paul Dirac. Nature is inherent in the fundamental feature that the most basic physical laws are described. Mathematical theory apparatus which possesses extraordinary power and beauty, but also universality. Mathematical science has a downside: it can seem cold, sterile, devoid of passion and feeling. As a result, it may turn out that although intelligent beings from other worlds and use the same mathematics, look at them, and this is not the best language for communicating on topics that concern us. Many suggest using mathematics to communicate with aliens, commented on the situation researchers from the Institute for the Search for Extraterrestrial Intelligence Networks, Seth Shostak. Moreover, the Dutch mathematician Hans Friedenthal even developed a whole language for this link. As however, Shostak continues, I personally believe that in the language of mathematics it will be difficult to describe such concepts as love or democracy. Any science, physics, certainly strives to ultimately reduce what it observes in the surrounding reality to a mathematical description. Specialists in cosmology and physics, elementary particles, and similar disciplines rejoice like children when they manage to measure or express something quantitatively and then find a dependence between these quantities. The idea that the universe in its basis mathematical has ancient roots and goes back to the Pythagoreans and even to in earlier period. Even Galileo saw the world as a great book written in the language of mathematics, and much later in 1960, the Hungarian-American physicist mathematician Eugene Wigner wrote an article entitled The Incomprehensible Effectiveness of Mathematics in Natural Sciences. In nature we do not encounter numbers directly, therefore it is not immediately obvious that mathematics is in everything that surrounds us. To see this, you can, for example, read a book, Mathematical Component. Editor and compiler Andriy Konovalov. Banya him, but we see geometric forms, almost exact spheres of planets and stars, curved trajectories of thrown objects and objects moving in orbit, symmetry of snowflakes, and much more, and they can already be described using numerical relationships, and besides they also have regularities which can also be translated into the language of mathematics in the work of the electric and magnetic field, in the rotation of galaxies, in the behavior of electrons in atoms. These regularities describing their equations substantiate individual events and phenomena and represent deep timeless truths, underlying the constantly changing, complex and multifaceted world in which we all exist. German physicist Heinrich Hertz was the first to convincingly prove the existence of electromagnetic waves. Wrote that it is impossible to get rid of the feeling that mathematical formulas exist independently of us and have their own mind. That they are wiser than us, wiser even than those who discovered them, and that we extract more from them than was originally laid down. There is no doubt that modern science has a solid mathematical foundation, but this does not necessarily mean that reality itself is a mathematical science in its essence. Since the time of Galileo, science has divided subjective and objective, or measurable, and focused on the latter. Scientists do everything possible to exclude any factors related to the observer and take into account only what they believe is beyond the interference of our brain and senses. The entire path of development of modern science practically guarantees that it will be based on mathematics. But then you are left overboard with many areas that are not so easily subject to scientific analysis. The most obvious of them is consciousness. For what purpose in the process of evolution the human brain has developed such outstanding abilities for? Absolutely not. It does not need mathematics for survival. Maybe someday we will build a good comprehensive model of the work of the brain, having understood all the nuances of the functioning of memory, processing visual information and much more, but the question of why we are also given internal experience, the feeling of what it is like to be, remains and perhaps will always remain outside traditional science and therefore mathematics. On the one hand, there are supporters of Platonism considering mathematics an already existing theory that is just waiting for us to research it. On the other hand, there are those who claim that we invent mathematics gradually as the need for it arises, and both points of view have weaknesses. Platonists are unable to explain exactly where, outside the physical universe and the human mind, such things as the number pi exist, and their opponents cannot deny the fact that the planets, for example, will revolve around the Sun in an elliptical orbit regardless of our mathematical calculations. The third school of philosophy occupies an intermediate position, and its representatives believe that mathematics is not nearly as effective in describing the real world as sometimes try to imagine. Equations help us direct a spacecraft to the Moon or Mars, design a new airplane, or predict the weather for several days in advance. But these equations are merely approximations of the reality that they are intended to describe. Moreover, they apply only to a small part of the phenomena occurring around us. In extolling the successes of mathematics, a realist would say, we beg the value of a huge number of phenomena that are too complex or poorly understood to fit into mathematical form, or, by their very nature, are not amenable to such analysis. Or perhaps in fact the universe is not mathematical by nature, after all. Neither in space nor in the objects contained in it there is nothing clearly mathematical. We humans try to give a rational explanation for the phenomena we observe, to simplify them in order to model some aspects of the structure of the universe, and mathematics provides us with invaluable help in understanding this very universe. But this does not necessarily mean that mathematical science is something more than a tool created by us for our own convenience. However, if mathematics was not in the universe initially, how did it happen that we were able to invent it and apply it for such a purpose? All mathematics can be roughly divided into two areas, applied and pure. The term pure mathematics is attributed to Godfrey Harold Hardy, who believed that mathematics pure from applications is the most beautiful. And applied mathematics is trivially ugly or boring. Pure mathematics is science for science's sake. Applied mathematicians use their knowledge to solve practical problems, but often the achievements of pure mathematics, seemingly having no practical application, later turn out to be surprisingly useful for practical scientists and engineers. In 1843, Irish mathematician William Hamilton formulated the idea of quaternions, generalization of ordinary numbers to four-dimensional space. At that time they did not represent any practical interest. But more than 100 years later they found wide application in robotics, computer graphics and video games, the problem of dense packing of spheres in three-dimensional space, which Johannes Kepler first attempted to solve in 1611, is used to more efficiently transmit information over noisy communication channels. Research in number theory, the purest mathematical discipline which was considered to have almost no practical value, led to important discoveries in the field of developing cryptographically strong ciphers, and the new geometry of Bernhard Riemann, who studied curved surfaces more than 50 years later, turned out to be the ideal basis for creating Einstein's general theory of relativity. New theory of gravitation. In July 1915, one of the greatest scientists of all time, Albert Einstein, visited Verden Ghent University, where he met with one of the most outstanding mathematicians of that era, David Gilbert, and in December of the following year irradiated, almost simultaneously published, the equation describing the gravitational field in Einstein's general theory of relativity. But if for Einstein the equations themselves were the goal of his work, then Gilbert hoped that they would be a step towards implementing an even more grandiose plan. He was driven by a passionate desire to find fundamental principles or axioms underlying all mathematics, for according to Gilbert, it was necessary, among other things, to formulate a minimal set of axioms from which it would be possible to derive the equation not only of Einstein's general theory of relativity, but also of any other physical theory. Kurt Gödel. With his theorems they completely undermined the belief that mathematics is capable of giving answers to all questions, and to this day it remains unclear to what extent the world in which we live is mathematical, or is it just an appearance. Entire sections of mathematics may never find practical application, but will only lead to the discovery of ever new directions of fundamental research. On the other hand, who knows, maybe the laws of pure mathematics act in some unexpected way in the physical universe, if not in ours, then in some other universes that make up the suspicion of cosmologists, a multiverse of incomprehensible scale. Maybe everything that is true from the point of view of mathematics somewhere, sometimes somehow represented in the reality in which we are enclosed. Well, and for now we will go on a fascinating journey through the vastness and knowledge, exploring new frontiers of numbers, space, and the human mind. Yes, some things in mathematics may seem abstruse, far-fetched, or even meaningless, and such strange and tangled play of the imagination. But at its core, mathematics is a science practically rooted in trade, agriculture and architecture, and although in its development, it has undergone a transformation that our ancestors could not even think of still in their heads, in its essence it remains closely connected with everyday life. How to see four-dimensional space. One of the strangest features of string theory is that it requires the existence of more spatial dimensions than the three that we directly observe in the world around us, reminiscent of science fiction, and nevertheless it is an indisputable fact arising from the mathematics of string theory. Brian Greene. We live in a world of three dimensions: up, down, right, left, and forward, backward, or any other three directions located at right angles to each other. You can easily imagine something one-dimensional, for example a straight line, also from a two-dimensional object, say a square drawn on a piece of paper. But how can you learn at all see in addition to the dimensions we are familiar with? Another, where is the additional axis located perpendicular to those that we already know? These questions may seem purely speculative, because in our world there are only three dimensions. So why rack your brains and worry about 4, 5, and so on? The point is that additional dimensions may be needed by scientists to explain what is happening at the subatomic level in these additional dimensions. Perhaps the key to understanding the great law of matter and energy is hidden it on a more practical level. Four-dimensional vision could open up enormous opportunities in medicine and education. Sometimes the fourth dimension is interpreted not simply as an additional axis in space after all. It is possible to measure not only space physicists, for example, the basic dimensions, the building blocks from which other quantities are built, are length, mass, time, electric charge. In other contexts, physicists often talk about three spatial dimensions and one time dimension, especially since Albert Einstein proved that in our world they are always connected into a single whole called space-time. But even before the theory of relativity, people have speculated about the possibility of moving forward and backward in the time dimension, just as we can move freely in space in the novel Time Machine. Published in 1895, Herbert Wells explains, for example, why there cannot be a timeless cube observed by us moment by moment. A cube is just a projection of a four-dimensional body having length, width, height and duration of existence. The only difference between time and any of the three spatial dimensions, says the time traveler, is that our consciousness moves along it. The idea of a fourth dimension of space aroused the keenest interest in the Victorian era, and not only among mathematicians. Followers of another widespread fascination of that time, spiritualism, also took it up at the end of the 19th century. The loud statements of mediums and the prospect of communicating with the dead attracted many people, including such celebrities as Arthur Conan Doyle, Elizabeth Barrett, Browning, and William Crookes. And suddenly people began to think that the afterlife exists in a fourth dimension parallel or intersecting with ours, and the spirits of the deceased can freely move into our material world and back. Due to the inability to imagine how bodies might look in a more multi-dimensional world, we are tempted to consider the fourth dimension as something mysterious beyond the world we know. But for mathematicians, working with four-dimensional objects and spaces does not cause any difficulties in order to describe their properties. A mathematician does not need to imagine how those look. These properties can be calculated using algebra and mathematical analysis without resorting to any multi-dimensional mental tricks. Let's take a circle, for example. A circle is a curve consisting of all points on a plane located at the same distance, called the radius from a given point center. As in a straight line in a circle, there is no width or height, only length, and therefore the circle is one-dimensional. Imagine that you are on a line and limited, and by the limits you can move along this line either in one direction or in the opposite direction too from a circle, even though it exists in space having at least two dimensions. But if you are located on it and it is already limited freedom of movement, you have no more than on a straight line, only there and back along the circle that is actually one dimension. Not mathematicians sometimes confuse a circle with a circle, but for a mathematician a circle is a completely different object. That includes this that is within circles. A circle is a one-dimensional figure that can be embedded in a two-dimensional object, a plane. This can be depicted in a simplified way by drawing a circle with a thin pencil on a sheet of paper. The length of a circle is 2 pi, where its radius and the surface area of a circle bounded by a circle are calculated using the pi² formula. Moving one dimension higher, we get a sphere consisting of all points lying at the same distance from a given one, but already in three-dimensional space. And again, a person far from mathematics can confuse a sphere with a two-dimensional surface, a ball that also includes all points located inside this surface.